you don't understand sinking and floating. No, it wasn't enough to get this in the 4th grade. It turns out on the final exam, the problem that is most often missed is the problem on fluids. The problem that's hardest on that exam will be the problem on fluids. So I am trying to convince you that there's part of this you still need to learn. Now, to get us up to the place where we can start doing the hard problems, we got to race through some background. We got to race through some concepts that maybe review for you. And we're going to do that very, very quickly with a lot of short exercises where you'll be working with your neighbor. So really quick, if you could just reintroduce yourself to your neighbor, and this time find out their middle name. What is their middle name? Still human?
Huh?
Still human?
Still human. Just got out of here. I'm late because of a small engagement that had me tied up near Hamilton.
Okay. Some of you are sitting next to someone that doesn't have a middle name. We named our daughter Heidelinda just because I like the name, and Heidelinda is a long enough first name. We didn't give her a middle name. It seemed cruel. So if you're sitting next to someone who doesn't have a middle name, just call them Nimrod. Nimrod. No, it's okay. It's biblical. It means mighty hunter. There's no greater thing you can call someone in Montana than Nimrod. You try it down at the gun club. Hey, Nimrod. Pass me that gun clip. Yeah, see if that works. Okay, homework. 2, 3, and 4 are pretty straightforward, but they're in chapter 10. We're skipping to chapter 10. We'll go back and pick up chapter 9 next week. Okay, let's collect some homework. Oh, just kidding. Can't do it. Just messing. Okay. Okay, turn to Nimrod and answer this question. How do you find the area of some surface? Just tell Nimrod how you do it. How would you do it? Okay. Is anyone sitting next to a Nimrod that came up with length times width? Okay. Have I got a deal for you? On the side, I also have a job selling real estate, and I happen to have 2 properties, 2 farms. They're each $1 million. They're a steal. And both of these farms are exactly the same as far as the water and the dirt and the farming stuff. I'm a city boy. So we just want the biggest farm, the one that's got the most area. And so if we look at farm number 2, and we apply the formula length times width, we get the area. But as you can see, that's not the farm you want to buy. You want to buy that farm because, man, lots of length, lots of width. So clearly this formula works for rectangles, but not so much for odd shapes. What are we going to do in a case of an odd-shaped farm? Yeah, put it in a grid. Okay, if each of those squares represents, say, an acre, then for farm 2, there'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19. Yeah, clearly there's a faster way to do that when you've got a rectangle. If I just count 8, and 1, 2, 3, 4, 5, 6, 7, 8, I can multiply. That's just a fast way of adding the same thing over and over again. And that's why length times width works for a rectangle. But if I'm trying to find the area of this farm number 1, I got to go 1, 2, 3, 4, 5, 6, 7 and a half, and 2/3, and 3/4. I got to add them up. Now we're not going to need to know how to calculate the area of something. What we would like to do is calculate the volume of something. Something that has an irregular shape. And I suggest to you that this guy has an irregular shape. Not an uncommon shape, but an irregular shape. Would you agree? It's the shape that all of us are going to assume at some point in our lives. Trust me. Okay, now if I wanted to find the volume of that guy, I could do it by taking these cubes here. These cubes are exactly 1 centimeter by 1 centimeter by 1 centimeter. We call them cubic centimeters, strangely enough. And if I were to build a block, I mean, this would take me forever. We don't have that much time together. But if I were to build me a block out of these, someone here at the university actually spent your tuition dollars on these cubic centimeters. They really did. I found them in a drawer over in the lab room. Not my fault. But if I made a block out of these, and then I carved an exact duplicate, I took out a carving knife and carved an exact duplicate of this little guy, then I could pull apart the cubes and count them. Being careful to say, you know, this is only half a cube, this is a third of a cube. And that way I could find his volume. Now conceptually, that's a very easy idea. But in practice, that would really be hard. First of all, I'd have to be a really master carver to make an exact duplicate, and then I'd have to count all the squares. In order to suggest another way, I'm going to show you a demo that I call the 75-25 rule. And that's because my experience has been, over the many years, that when I show you this demo, 75% of you think, oh yeah, I've known that since the 3rd grade. That's obvious. And 25% of you have a mind-altering experience. Just, whoa, whoa. Now here's the thing. You should have had this experience in the 3rd grade. So when I do this demo, regardless of which group you're in, act bored. Okay? Act bored. Now, I have 2 identical cubes. They're both exactly the same size. They're both painted black. They're identical, are they not? Are they?
No.
No! Okay, she says I'm lying. Who are you going to believe, me or her?
Me.
Okay. One of them is made out of steel, and one of them is made out of aluminum. One is a lot heavier than the other. Now, I'm going to take these 2 cubes and I'm going to lower them into this colored water. And the question is, in which beaker is the water going to be displaced the most? In which beaker is the water going to go up the most? Now, folks, during this demo, do not make eye contact with Nimrod. Do not look at Nimrod. Pretend you're bored. They go up the same. Of course they do. I knew that. I knew that. Because where the block is now, water used to be. And it had to go somewhere else. Has absolutely nothing to do with how heavy they are. Has everything to do with how much space they take up. The volume of the object. And this gives us a second way to measure volume. If I submerge an object in a liquid like water, the volume of the object is displacing liquid. It will be equal to the volume of the displaced liquid. And by displaced we mean moved up. Now this is a principle that was not always fully appreciated. It took a very, very brilliant man, Archimedes, to come up with this idea. I didn't learn it from Archimedes. I'm not that old. I learned it from my grandmother. one of the smartest people on the planet. She never went to college, but she could make a mean apple pie. And I lived in her basement for a while, and I said, Grandma, teach me how to make an apple pie. I want to be able to make an apple pie like you make it. And so she taught me that the key is the crust. If you can make a nice flaky crust, you are going to find yourself a wife. Man, listen to what I'm saying here, okay? Now, the key to a nice flaky crust is getting just the right amount of Crisco. My grandma said, get me a cup of Crisco. So I got a measuring cup and I started scooping Crisco. You know what Crisco is. It's just that, well, it's lard. Okay. I started scooping Crisco into the measuring cup, and I was having a hard time because there's air pockets, and you're kind of pushing it in to make sure you get all the air pockets out. And my grandma actually laughed at me. It's the only time she ever ridiculed me. She's a wonderful woman. And she said, Greg, that's not how you do it. And she filled up this measuring bowl about halfway, and she started throwing in Crisco until the water level went up 1 cup. And I said, Eureka. Eureka. Okay? Now, the first person to come up with it, oh, and I can make a pie. That's a pie I made. Okay. Oh, I figured out who the geeks are. Yeah, you saw it, didn't you? Okay. Yeah, okay. Geeks in the room. Okay. This is a story of hero Syracuse, the king, and Archimedes. You've heard it before, but I'll read it to you again. It's story time. So hero of Syracuse wanted to make a beautiful golden crown to the gods and put it in the temple. He measured out a certain mass of gold, gave it to the artist, and said, make me the most beautiful crown ever made. The artist returned a while later with a beautiful crown. It had exactly the same mass as the lump of gold. But Hero was worried. He suspected that maybe he had been cheated by this artist. Why? Because he was an artist. And he suspected that the artist had slipped in some silver and kept the gold. So he called in the local smart guy, Archimedes, and he gave him the job of figuring out whether the crown was pure gold. As the story goes, Archimedes was pondering on this. He went down to the bathhouse, and as he lowered his considerable self into the tub, water splashed out onto the floor. Suddenly he had this brainstorm. As the story goes, he leapt out of the tub, ran naked through the streets of Greece, which is not really that uncommon, and he was yelling, Eureka, Eureka. So he goes back to the king, and he does the following test. He takes a lump of gold that's the same mass as the crown, a lump of silver that's the same mass as the crown. He first of all places the silver lump into a bucket of water and measures carefully how much water spills out. He does the same with the lump of gold, and finally with the crown. How does this story end? Anyone know? The artist dies. Yeah, he cheated the king. He lost his head. Okay, let that be a lesson to you. Don't go into art. Okay, new topic, density. Density is very simply the amount of mass in 1 unit of volume. And the unit that we're going to use is 1 centimeter by 1 centimeter by 1 centimeter. Now, folks, this is an exception to the rule. Typically in a science class, we use MKS units. And that turns out to be the easiest way to work problems. But when it comes to density problems and sinking and floating problems, it turns out that meters cubed are not a convenient unit to use. Centimeters cubed are a better unit. And we'll see why that is in just a moment. But if I wanted to know the density of this little man, what I would do is take a pocket knife and cut out of his backside a cube, 1 centimeter by 1 centimeter by 1 centimeter, of him. And then I would find the mass of that cube, and that is, by definition, the density of that substance. It's a property of a substance. There's a density of gold, there's a density of silver, there's a density of platinum. Okay. Does anyone know the density of water? 1 point what? 1 point what? 1.0 what? 1.00 what? 1.0000 to infinity and beyond. That seems like quite a coincidence. That seems unlikely. It turns out that it is 1 by definition. The meter had already been defined. There are a certain number of meters that got you from London to the North Pole. The meter was already defined, and hence the centimeter was already defined. But the gram, 1/1000th of a kilogram, the gram was defined as the mass of water that would fit in 1 centimeter by 1 centimeter by 1 centimeter. But it couldn't just be any water, it had to be special water. What had to be special about it? Help me out. Raise your hand, Ray Soul.
Distilled.
Distilled water turns out that's good but not critical. Something else had to be. Deionized? Well, yeah. Usually it is, but it's not critical.
0?
It had to be a certain temperature. And your gut tells you that it ought to be 0. And the actual answer is 4 degrees Celsius. Whoa! But that's what keeps this planet alive, people. Most liquids get denser and denser as they get colder and colder. And water does that to a point. But when it gets to 4 degrees Celsius, instead of continuing to get denser, it expands and gets less dense. That's what allows the rivers, the lakes, the ponds to live through the winter. If water was like other substances and it just got denser and denser down to 0, then our lakes would freeze from the bottom up, because 0 would be the most dense temperature. But it turns out that 4 degrees is the most dense, and it sinks to the bottom, and that allows the 0 degrees at the top to form a layer of ice, and that protects the lake from the cold, and it keeps the fish alive. Okay, keeping the fish alive, that you gotta admit, that's important. That's big. Okay, that brings the tourists. Now, if you want to win a game of what's that game where you got facts? You gotta. What's that? Trivial Pursuit. Thank you. Okay. If you want to win a game of Trivial Pursuit, cheat. Pick up the card and pretend to read it, but instead ask your opponent, what was the temperature at the bottom of Lake Tahoe on the 13th of July, 1872? Just make up a date. Just make up a date. The answer is 4 degrees Celsius. It is always 4 degrees Celsius at the bottom of Lake Tahoe. It never, no matter how hot the summer, gets hot enough to heat that up above 4 degrees Celsius. Okay? You're always going to win. You're always going to win. Now, the fact that that density is 1 gram per cc is what makes it so convenient to work problems in these units, grams per centimeter cubed. And you need to know that we try to trick you. That sometimes we write this as 1 gram per centimeter cubed, and sometimes we write it as 1 gram per centimeter cubed, and sometimes we write it as 1 gram. Anyone know? Any nurses? Milliliter. Okay? It's all the same. It's all the same. Now in the actual units, the MKS units that we're supposed to use, the density would be 1,000 kilograms per meter cubed. Now what that means is that in a chunk of water that is 1 meter by 1 meter by 1 meter, there would be 1,000 grams that'll weigh a ton. And that's why your landlord doesn't want you to have a water bed on the second floor, okay? Water's pretty dense, pretty dense. Now this is the type of density question you could expect on the final exam. A 50 centimeter cube piece of magnesium has a mass of 87 grams. What's the mass of a 6 centimeter cube piece of magnesium? With Nimrod, come up with an answer, please. With Nimrod. Okay, let's talk about it. One way to solve this is to say 87 grams is to 50 centimeters cubed, as x grams is to 6 centimeters cubed. How many of you are sitting next to a Nimrod that was doing it that way? Okay, that's a perfectly acceptable way to do it. If you do it on the exam that way, fine. However, if you are planning to be a teacher, a high school teacher or a junior high teacher, first of all, let me just say I love you. I mean, I love all of you, but I love them a lot more. Okay, becoming a high school teacher, junior high teacher, it's the most noble thing you can do. I mean, almost anyone can be a doctor and take people's hearts and fix them, but you know, to teach kids, that's amazing. If you are going to be a teacher, I beg you, I plead with you, don't do it this way. If you're going to be a teacher, I would ask you to do it in 2 steps. I would ask you to first of all define the density, we use the simple rho for density, of magnesium. And that would be the total mass divided by the total volume. And that would give you 1.74 grams per centimeter cube. Only I would beg you again not to pronounce it that way. Instead say 1.74 grams for each centimeter cube. Always, whenever you're teaching, grams for each centimeter cube. And if I want to know the mass of 6 centimeters cubed, well, that's how much mass there's in 1 centimeter cubed. I just add that up 6 times. But when you find yourself adding the same thing over and over again, that's a good time to multiply. Okay? I have 1.74 grams for each centimeter cubed, and I have 6 centimeters cubed. And that's going to give me 10.4 grams. If you teach your students to do it that way, you will develop in them proportional reasoning skills that will benefit them as they go through all of their science classes throughout their life. And you'll be doing them a favor. Okay, let's just see how well we learned this idea of density with your clicker. These are not hard questions, these are just questions. Which has the larger density, a cup full of water, a lake full of water? Okay. And the answer is the same. The same. Oh, gee, if it weren't for these 2 people, we would have gone to Disney World. Oh, well. Now, that's assuming that the lake and the teacup have the same temperature. And in this class, we're always going to assume that the temperature is uniform so that we don't have to worry about the change in density with temperature. What about this one? This one's even easier. Which has a greater density, a kilogram of lead or a kilogram of feathers? Okay. And it is a kilogram of lead. Okay, again, density is a property of a substance. It doesn't matter how much lead you got. You could have a tiny, tiny little drop of lead. It would have more density than any amount of feathers if you filled the whole room with feathers. Okay, so it's a property of the material, of the substance. Okay, we're going to talk about fluids, by which we mean liquids and gases, and we're going to start with liquids. Now, a fluid can conform to the shape of its container, but a liquid takes the shape of the container without changing its volume. And that proves, by that definition, that cats are liquid. Hey, the cat's fine. The cat's going to be fine. Okay. So let's talk about liquids. Have any of you scuba dived? Yeah, okay. Now scuba diving is way fun. I went to high school in Guam, and that's what we did after school. Our physics teacher had only had one class of physics in his whole life. And he taught us what he could. He taught us a little bit of physics, and when he ran out, he showed us the most wonderful pictures of sharks. And that's what I learned in high school physics. And he was also the faculty advisor for the scuba club. And so we would go after school and go scuba diving and snorkeling. Now, if your ears get clogged or you have a hard time with your sinuses and you go down snorkeling or scuba diving, what happens? Yeah, it feels like your head's going to explode. It feels like, you know, you're being crushed. Okay, and that's this pressure of the fluid around you. Now, earlier in the class, we defined pressure as the force applied divided by the area over which it's applied. And with a liquid, we just need to modify that definition slightly and say that this is the component of the force that is perpendicular to the surface that we're finding the pressure on. Now let me see if I can give you a visual for that. Many, many years ago when my children were young, my father decided to take all of his posterity to Disneyland on a very hot August day. He didn't decide to pay for it, he just decided to bring us all. I paid a fortune to get my family into Disneyland. And it turns out that when we got there, we found that every other American family was there with us, and a lot of families that were from other countries. And during the course of that one very long, very hot day that I paid a fortune for, my family got on two rides, and one of them was Dumbo. And the other one was 20,000 Leagues Under the Sea. Does anyone remember that ride? It doesn't exist anymore. They got rid of it finally. It's replaced with Nemo. But at the time, they had this great big, huge swimming pool and a submarine. And you waited in line for 5 hours to get on this submarine, and the submarine took you on this journey. And it dove down 20,000 leagues under the sea, except for 5 hours you were watching it just go around on top. And everyone had a little porthole that they could look out of. And if you look out that porthole, you saw these wonderful, beautiful fish that were plastic. And they were held to the bottom of the swimming pool with fishing line. I don't know what Walt was thinking, but this was not a Disney ride. Anyway, if you think of that circular window, there's two pressures on it. You got the water pushing in, and if you take the total push in and divide by the area, pi r squared, you have the water pressure. And then you got the air pushing out. Now, clearly they had to pressurize the submarine because we were going so deep. But the air pushing out, you divide that by pi r squared, and you get the pressure, the air pressure, going the other way. Okay? Now, what should matter? We already said that the deeper you go down in water, the bigger this pressure becomes and it starts to make your head feel like it's being crushed. What else should matter besides how deep you go? Brave soul, raise your hand. Come on.
How much is pushing on you?
How much
Is pushing on you.
Yeah, how much water is above you, okay, and that has to do with how deep you go. Or you mean the surface area of the body of water, like whether it's a lake or whether it's a pond?
No.
Okay. What else? What else should matter?
How fast you go down? How fast you go down?
How fast you go down is going to determine how bad your headache is and how quickly your head explodes. But fortunately, that's not going to affect how big the pressure gets. No matter how fast you go down to 100 feet, it's still going to be pushing on everyone the same down there.
How big you are?
How big you are, okay, that will have to do with the total push, but not the pressure.
How much area it's pressing on?
That's how big I am. The density. Whether you're going down in a pool of fresh water, or whether you're going down in a pool of salt water, or whether you're going down, heaven forbid, in a pool of liquid mercury, okay, it matters. Now, so the only two things that we find matter are how deep you go and the density. Now, how deep you go can easily be demonstrated with this cylinder. It has some holes drilled in the side, and you can see that the deeper in the water, the greater the pressure with which it's streaming out of the hole. And that demo is just disconcerting. That's just going to distract us and make us uncomfortable until I get rid of that. Let's just stop that. Okay. Now, my good friend Jeff Adams, when he was a teenager, and he was a geek, he was bound to be a physicist, his family bought a summer cottage on a lake in Canada because they're Canadian. And he got to that lake and decided, I want to explore that. And so he decided he was going to explore the entire bottom of that lake. And the way he was going to do it, he felt, was ingenious. He didn't have any scuba gear, but he did have a scuba mask. And he found a way to weight his feet down. So he put on that mask, and he weighted his feet down, and he was going to walk across that lake on the bottom. And first, he went and got the garden hose, and he hooked the garden hose to a big piece of styrofoam. And he was just going to breathe through that hose as he walked across the bottom of the lake. And he was really surprised that Jacques Cousteau had not come up with this before. It just seemed so obvious. Now, it turned out badly. Anyone know why?
His lungs don't have the strength to push air all the way out.
Exactly. The lungs do not have the strength to push air or to bring air all the way down. If I look at the pressure at the two ends of that hose, there's much more pressure on the bottom of the hose than the top. Which way is the air going to flow through that hose? Up! This is a great method for getting all of the air out of the Jeff. And that's what it did. But that wasn't good. Okay, so that is not a good plan. Okay. Now, let's find a formula for the pressure in a fluid at a certain depth. Now, this is a little bit of a derivation. It's not going to hurt. It's not going to take long. It's going to be really quick. What we're going to do is we're going to go down to the local pond, Bozeman Pond, and we're going to carve out mentally with our mind a block of water, a chunk of water. And we're going to draw a free body diagram for that chunk. Now, there's lots of forces on that chunk, sideways, but there's only three forces that act vertically. There's the weight force, the non-contact gravitational force, the mass of the chunk times g. And then there's a force pushing up from below, the water beneath this chunk, and there's a force from the water above pushing down. Now in both of those cases, I can write them as the pressure at that point, that's how much force there is per unit of area, times how many units of area I have on that chunk, top and bottom. Now if I balance all the forces, and why would they be balanced?
Not accelerating.
Because that chunk doesn't know he's special. He doesn't know he's different from the neighbor chunks. He's just sitting there with his brother water. Okay, he's not going up, he's not going down. So that free body diagram has to scream balance. So the one force up has to balance the two forces down. Now I'm just going to meddle here. I can write that mass as the density, that's the number of grams in 1 unit of volume, times the volume. How much mass there is per unit of volume times the units of volume. I can write that volume for this cube, this chunk, as the area of the top and bottom times the height. And now you see that every term has the area in it. I can divide both sides by area, and I get the grand high equation for pressure in a fluid. I'm going to write it over here. The pressure at any point 2 is equal to the pressure at any point 1 plus 3 things multiplied together, rho, g, h. Now, as long as I know the pressure in the fluid here, I can use that formula to find the pressure in the fluid there. And so what we find is that the pressure in a fluid really depends on 3 things. We said it only depended on 2, but we were making a very, very strong assumption. It depends on the density of the liquid, it depends on how deep you go, and the last one, it depends on what planet you live on. We assumed we were going to stay on Earth, and in that case it only depends on 2 things. But if you go to a different planet with a different gravitational field strength, you can go a different depth before your ears pop. Okay? Now, typically, in 99.99% of the cases, we choose P1 to be at the top of the lake. So what's the value of the pressure there at the top of the lake? Is it 0? It's 1. 1 what? Turns out it's 1, we call it an atmosphere. It turns out that when you're at the top of the lake, you are at the bottom of an ocean. A fluid is either a liquid or a gas. And when you're at the top of the lake, you are at the bottom of 30 kilometers of air. A vast ocean of air. Now in Bozeman, not really 30 kilometers because we're up so high, but still, it's a considerable amount. And so the pressure at the top of the lake is not 0, not even close. It turns out that it's 101,325 newtons for every meter squared. Now again, a newton is only 1/5 of a pound. It's not a very big force. And a meter squared is a big area. So this unit, although the official MKS unit, is pretty small. We call that combination Newton per meter square a Pascal, to honor a dead professor. Good thing to do. And typically, we work in kilopascals because a Pascal is so small. So we say that 1 atmosphere is about 101 kilopascal. And that's what they say in virtually every civilized nation on the earth, except one. America. Land of the free. We don't have to conform. What is 1 atmosphere in America? Anyone? No, 7. That was a really Really, really close. You were half right. Okay, it's not 7. It's 14.7 pounds per square inch. Pounds per square inch. What that means is that on every square inch of this milk carton, this great big sea of air is pushing with 14.7 pounds. Well, there's a lot of square inches on this thing. You'd expect it to just crumple right up. And it doesn't, because there's air on the inside as well pushing out in order to balance the push in. Now, if I were to take the air out of the inside with this pump, you can see that it doesn't take very long for that to just crumple up. Okay? Now, that's a plastic can. I assure you it works just as well with a metal can, but metal cans these days are used for paint thinner and things like that, and it's kind of hard to get those metal cans. Now, I was hoping to crush a 55-gallon drum. However, I had the 55-gallon drum, and then the junior high in Livingston called and asked if I would do a demo show for them. This was 3 weeks ago, and so I took my 55-gallon drum and I crushed it. That's the drum. Now, here's how I did it. I put a gallon of water in the bottom of that drum, and I put the drum on 2 hot plates for about an hour. And after about an hour, after about 40 minutes actually, there was steam coming out of the top. A lot of steam. Now steam is water vapor. It's water in the gaseous, it's gas water. So when that steam is coming out, it means the air has already been pushed out by the steam. The steam is now leaving, but the air left long before being pushed out by the steam. So once we get that steam coming out, we take the 55-gallon drum off the heat and quickly cap it off. Now you want to do it in that order. If you do it in the opposite order, it's a bomb. Okay? But you cap that off. And now you've got a 55-gallon drum filled with water vapor. And if you cool that drum down by throwing ice on it, the water vapor will turn back into about, well, half a gallon of water. But that leaves the rest of the space in there as a vacuum, with nothing pushing out on the can. Now, I was standing next to this thing, and it wasn't doing anything. It was just sitting there. And I thought, oh no, hundreds of people in this gymnasium, they're all watching. And I'm thinking, oh man, there's a leak. It's not working. Oh man. I was just about to apologize to everyone. I was just opening my mouth to apologize. And this thing just went, whoo! It just sucked in all at once. Just instantly it went to that. And they loved it. Those junior high kids, they loved that. They loved that. Now, years ago, we did that. To those who expected this can to crush and were disappointed because it did not, I'm trying to redeem myself. We're going to crush this can now. We've been boiling water for about 20 minutes. That boiling water is pushing all the air out of this can. And Trevor, would you come up and help me to take this off the heat and put it on some ice? Okay, put these on, please. And what we're going to do first is put some ice down on the floor. We'll clean it up later. Put a little ice right here. People don't slip on that after class. Now, it's important that we do this in the right order. I'm going to turn off the heat, and I'm going to cap this off. Would you hand me that wrench, please? Okay. Now, we're going to move this down onto the ice. Thank you. We're going to perhaps have some more ice. Cool it down on the fire. Science works.